All right, I had a couple examples left to go over on 5.3 and then 5.5 and 5.6. So the first one is just getting some extra practice with graphing with e to the x, which you have to use your calculator for. So we're just making a table of values. This should be a vertical shift of up 4 from the traditional e to the x parent graph. There's nothing happening in the exponent except for the letter x, so I can use my normal -2 to 2. So I'm going to be using my calculator to help me evaluate the following arithmetic. And e squared plus 4. So you would get your calculator out and you would use your second shift E button, whichever order you have to enter that in. And I'm going to do e to the -2 and then plus 4, and I get 4.14. Then I'm going to do e to the -1 plus 4 is 4.37. E to the 0 is 1, plus 4 would be 5. E to the first is 2.72, plus 4 will be 6.72. E to the second plus 4 gives us 11.39, which may be off our graph to the point where we won't plot that one. So we go to -2 up to 4.14, then -1 up to 4.37, 0, 5, 1, 6.72, and again, I'm not going to graph the other one because it's off the chart, but I'm headed that direction. Now, the thing to note is when you have a vertical shift, that changes your horizontal asymptote because you're shifting it off of that x axis. So the horizontal asymptote for this exponential function is y equals 4, which my computer screen jumped. Let me get down there. So y equals 4. The domain for any exponential is always all real numbers. The range is dependent on where our horizontal asymptote is, and if we're on top or bottom of that value, we are above 4. So from 4 to infinity, but not including 4. All right, and then the last one that I believe, let me double check. I think the last one we skipped in section 5.3 was the second graph underneath that, which is part D. This time when I'm choosing my table of values, I'm going to choose things that are going to allow me to center this exponent at 0, because e to the 0 is 1, and that's what we're trying to find, that point. So anytime you have anything added or subtracted or maybe multiplied in your exponent or divided, sometimes setting that equal to 0 will help you figure out what to plug in. So I'm going to start my chart at -4. And then we always pick 2 numbers smaller and 2 numbers larger. And if we've picked correctly, we should see some common things that we're used to seeing, like this is e to the -2. This one is e to the -1. E to the 0. E to the first, and e to the second. E squared is 7.39. Just from doing a lot of these, I kind of have these memorized, but you can use your calculator. E to the first is 2.72. E to the 0 is 1. E to the -1 is about 0.3. I think it was 3.7 or 3.9. Let me look up above. Yeah, 3.7. And then e to the -2 is 0.14. Again, you can check all of those on your calculator. So this graph has been shifted to the left 2 from the traditional exponential. And then through -3, 2.72, -2 is up here. So notice same shape as all of our exponential functions. This time the horizontal asymptote is still at 0. You only change that if you are shifting vertically. Domain is still all real numbers. Range is 0 to infinity because we're on the top half of that horizontal asymptote. All right, so that was it for section 5.3. We just had those 2 specific examples left. I'll make sure I get that reposted in the correct place in the weekly notes so that it has those 2 inks there. And then I'm going to switch my screen to 5.5 and 5.6. We left 2 at the very end to blank to do. I did one of every type in class, but I did leave one of them blank that was a change of base, and then another one that was like part B of 7 that we did together. And I did tell you that was an important one and to take good notes on it, so I wanted to do another one in the video. So this says, yes, evaluate this using change of base formula without a calculator. Well, obviously, if this was a calculator, you know, why would they have even chosen base 7? Because we don't have that base on our calculator. What you do notice is that the top base is the same as the bottom base on this log. That means you can do the change of base formula backwards. Remember, the change of base formula says we can take a log, I'll use B as the base, log base B of A, and we can convert that to any other log base we want on top and bottom, use the same base, but then we'll have the argument of the original in the top, and the base of the original is the argument in the bottom. So when we look at this, this is that same format. We can go backwards. This is our original base, this is our original argument. So I'm going to rewrite this. Sorry, that always does that. Lots to skip through. There we go. So it's going to be log of base 3. And I don't know why the ink's not working. There we go. Log of base 3 of 243. And if 243 has if it's 3 to some power, then we can then evaluate this log really quickly. So if you know 3 to the 4th power is 81, and 3 to the 3rd power is 27. And just to show you, let's see, 3 squared is 9. Trying to find the right power. 3 to the 5th, it'd be 81 times 3, because we're trying to do this without a calculator, and that's the one we needed. So that's 243. So if I can rewrite that argument as 3 to the 5th, then we had a property that says if a base on a log is the same as the base in the argument, the answer is just the exponent. So this actually evaluates to 5. And that's just using change of base formula backwards. We turned a change of base formula back into the original logarithm. Okay, the final example in this video is one where you have bases on each side and they both have a variable in the exponent. That's a big situation here, because normally if we just have one exponent that has an x in it, we can use our log definition and just turn this into a logarithm and then solve for the x. But because both bases are different and they'll never match and they both have an x, the best way to solve this is to take the log of both sides. So we're going to take the log of the left and the log of the right, and we use common log just because that's usable on our calculator. We will pull the powers to the front, so we're going to pull the 2x minus 3 to the front, and this would just leave us with log 4. Then we're going to pull the x to the front using our power rule for logarithms, and that just leaves me with log 5. I'm going to distribute the log 4 to both the 2x and the negative 3. Notice that's just a coefficient times a log. You can't distribute that to the actual inside of the log because that's an argument. And then we'll bring this down. Okay, then we're going to get all the x terms on the same side. So notice this term right here has an x. This term right here also has an x. This term does not have an x. I'm kind of color coding them so you can see them. So what we're going to do is we're going to add the 3 log 4 over, subtract the x log 5 over, just like we were moving terms in an algebra problem, because this is essentially solving an equation. So if we move the x log 5 over, we're subtracting it. If we move the negative 3 log 4 over, we're adding it. Once you get this over here, notice the x in both sides can be pulled out as a GCF. So x 2 log 4 minus log 5 equals 3 log 4. We can divide the parentheses to the other side. Now, usually this is fine for us. This is a correct version of that answer, but they do, so this would be an exact answer. This is technically an exact answer. We solve for x. X is all by itself. Now, the only problem is they also want a 2 decimal approximation. So it's better sometimes to simplify that down a little further. I told you it wasn't required, but it'll help you. So we can put the numbers in front of each log back up as a power. So this would become log 4 to the third over log 4 squared, because we're moving the 2 back up, minus log 5. You can work out each of those individual in pieces. So that'd be 64 if we cube it. This would be 16 minus log 5. Now there is subtraction in the bottom. That means we can turn that into division of the arguments. So that would be 16 divided by 5, and it would now be 1 logarithm. This is easier to type into your calculator, honestly, if you're trying to get the decimal approximation. So I prefer that. I think WebAssign will accept either version, but this is the easier one to get the decimal. So log of 64 divided by 16/5 log, and then that gives me 3.58 to 2 decimal places. So that is the approximate. Now this is also exact, and I personally prefer this version. That's not the word exact. Sorry, my pen's lagging, so it's hard to see what I'm writing. This is also exact, and it's better in terms of calculating the decimal, and it looks prettier. But I also accept this version over here that I've circled from students. So that is the end of the video. That's everything that I needed to finish up for you guys. And let me know if you have any questions.